Alright, welcome everybody. So today we're going to talk a little bit about covalent bonding. I'm going to try and teach you how to draw Lewis structures for covalent compounds. So before we get into Lewis structures though, let's talk a little bit about what a covalent bond is. So here I'm showing you two chlorine atoms on the left, and they're coming together to form a chlorine molecule, Cl2. So there's something important about this. When you bond, you have something called shared pairs. Covalent compounds, they are similar to one another in electronegativity. Both of those nuclei are pulling on those electrons similarly, and so you end up with a situation where you have shared electrons. If you remember back to ionic bonding in the last video, there was a big difference in electronegativity. The atoms were very different, so the electrons end up being transferred. So this is really the major type of bonding that we're going to focus on. It's present in really millions of molecules. Usually it's between two nonmetals, but sometimes you could have a metal covalently bonding if it has a strong enough electronegativity. The electrons are shared. I always think together, like co-worker, cohort, meaning to share. So covalent bonding, they're sharing the electrons. There's two types of electrons, like I mentioned. There's the shared pair, which is here, and then there's also the lone pairs, which are here. We'll mention those again and again, shared pair, lone pairs. Now you can share up to 3 pairs of electrons. So you could have a 1 pair shared. This is called a single bond. You could have 2 pairs for a double bond, or you could have 3 pairs for a triple bond. Now what's holding these atoms together in a molecule? Well, it's the same thing that we've seen in ionic bonding. It's electrostatic charges. So here we have a situation where I show 2 nuclei, and the electrons between the nuclei are going to attract the electrons. So it shows the attraction in red here. And so what we end up having is the 2 nuclei attracting the electrons between them. There's repulsion going on as well, so the nuclei are going to repel each other. They'll reach a certain point called the bonding length, or the covalent radius, where when they bond together, what ends up happening is they form this stable compound or molecule. And it looks like this. Here's my 2 nuclei, and then here's the electrons. The electrons are between the 2 nuclei, and so that forms a stable compound. So something really important, and what's going to be the crux of what we're going to do for the next couple of videos, is Lewis structures. So I'm going to take you through these instructions. You need to memorize these instructions. You need to use them when you do any Lewis structure for covalent compounds. Ionic compounds, it wasn't a big deal, but with covalent compounds, you need to know these steps. So here are the rules that we have. So first thing that we're going to do is we're going to count the total valence electrons for all atoms before they bond. The second step, we're going to put the atom that there's less of as the central atom. We're going to place single bonds between the atoms. Those bonds count for 2 electrons. Then we're going to make all the atoms have an octet, except for things like hydrogen, boron, and beryllium. So then we're going to count the electrons. We're going to make sure that the electrons in the structure match the original valence number. If not, we're going to form double bonds. But if there's too many, then we're going to do something called an expanded octet. So let's actually try this. Let's apply these rules here. So let's try something like PCl3. So the first step says to count the total valence electrons before bonding. So P has 5, and Cl has 7, and there's 3 Cls. So together, these have 26 electrons. Now, the next step says to put the atom there's less of as the central atom. So there's less P's here. There's only 1 P. So we're going to put the P in the middle, and the Cls are going to go around it. We're then going to place single bonds between them, and each of these bonds counts as 2 electrons. So we're going to have 1 bond, 1 bond, 1 bond. The next step says make sure all atoms have an octet. None of the exceptions are here, so this Cl needs 6 more. Now it has a total of 8. 2, 4, 6, and 1 bonding pair or shared pair makes 8. The Cl on the bottom, 2, 4, 6, gives us 8. The Cl on the left, 2, 4, 6, 2 in the bond make 8. And the P, 2, 4, 6, 7, 8. So now I've done my structure, But now I need to do step 6. I need to count them, make sure that they match the original. So I go ahead and I do that. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Let's count again because there should be 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So here's my complete structure with 26. This is a completed Lewis structure. Each of the elements has 8 valence electrons total now that it's bonded. And we have this situation where it matches the total number. Let's try something where it may not work out so well. Something like SO2. So now I count up the electrons again. S has 6, O has 6, times 2, so that gives us 18 electrons. Now I go ahead and I draw my structure. S in the middle, single bonded to O's. Give each one 8, so this O on the left needs 8. This S in the middle needs 4 more. This O on the right needs 8, so 6 more. I count them up. When I count them up, I get 20. That's too many. So if we go back to the instructions, it says, if not, with step 6, if not, then form one double bond. So I'm going to redraw this instead of trying to fix it. You should always redraw it instead of trying to fix it. S, now we're going to do a double bond on this side, and a single bond on this side. I go through and I put in my dots, and I want to give each one 8. So the O on the left, I make sure 2, 4, 6, 8. The S in the middle, 2, 4, 6, 8, and we could highlight that as I'm counting. 2, 4, 6, 8 for oxygen, 2, 4, 6, 8 for sulfur, 2, 4, 6, 8 for oxygen, and now I count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18. I can do that in a different color just to show you, what that looks like. 2, 4, 6, 8, 10, 12, 14, 16, 18. It matches the original number. This is the correct structure. Now if you don't like dots, you can do lines. So I could do like this. I could do like this. And so that's the same structure. So these are the Lewis structures. I said that there were some exceptions. Let me do those on the side here in green. So hydrogen, for example, it only has a 1s1 electron. So when it bonds, it will only ever form 2 electrons. Something like HCl, like this. It will form a bond like this. Notice the H does not have 8 dots. Beryllium is another one. Beryllium's a metal, but it actually covalently bonds quite a bit to things. And when I draw Be, it will only have the 2 bonds like this. And boron's a third exception. Boron has 3 bonds only, although it can form 4 bonds. But here I show you boron with 3 bonds. And so the rules for the exceptions, H has 1 bond, Be has 2 bonds, B has 3 bonds. All the other elements that we generally do will form an octet. What you're going to see, though, is that a lot of these elements, they violate. They can go above the octet number, and they can accommodate more electrons. We'll talk about that, too. So this is Lewis structures, and we're going to practice a lot of these in class, but this is a rundown. What you should spend your time doing, is memorizing these rules and make sure that you know them. So there's something that's going to come up here, and you can see it right here with SO2. If we look at SO2, some of you might be saying, well, why don't you draw the double bond on the other side? Well, I could have, and that's actually called a resonance structure. A resonance structure is where where you can actually move the electrons between atoms in a molecule. And this is very important because what this does is it spreads out the electrons. And if it spreads out the electrons, that will minimize repulsion. And it leads to an increase in stability. So what does this actually look like? Well, here's my, SO2 here. I could draw it like this with the double bonded like this. And then what actually is occurring is these electrons here can move into this part, and these electrons here can move out there. And what you'll be left with is you'll be left with S with a double bonded here and single bonded there. These are resonance structures of each other. Now the cool thing about resonance structures is the electrons are always moving. So you don't really have either of these structures. You actually have both of them at the same time, which I think is kind of neat. The electrons are free to move, so they can either be a double bond on the left or a double bond on the right. And what you end up with is kind of like a mix of the two. The most common molecule that does this, that's used a lot, is something called benzene. So what I'd like you to do is actually, Google benzene, find out what the structure is, and draw it for me. We'll talk about it in class. I'll put it as one of the questions. The next thing that I wanted to tell you about was formal charges. But what I'm going to do for now is I'm going to stop here because we've done a lot. And this is really enough for us to, go ahead and start our first part of our lab, which is building the structures. When I come back in the next video, we'll do some formal charges, we'll do resonance structures in more detail, and we'll talk about exceptions to the octet rule. All of this is really important because once you have this down and you can draw these Lewis structures, we'll start looking at things like, what is the shape of the molecule? And from there we can talk about all the other things that you need to know related to a Lewis structure. All right, thanks so much for watching and have a great day. Hope you're enjoying your weekend.